Welcome to this presentation. The topic is to illustrate C-shock capability, and for this we use a specific model we have built up for predicting shock machine response. You see the shock machine is used for testing aerospace equipment to high shock load, and presently this machine is made of table on which you bolt the equipment and on a big mass attached by a cable, and this mass is impacting the table with a high velocity and delivering a high level of shock on the equipment, and from this we will be able to compute the shock response spectrum of the equipment. This machine in brief have been built from scratch from a CAD file in two configurations, and in this presentation we will analyze the model of the two configuration where the table is horizontal. In that case the shock is applied in the in-plane direction, so it's more difficult for an SEA model to handle this situation. And you can see from the FEM calculation two different modes, fundamental mode of the system. And the mesh was built up for working up to 10K. Just a few explanations about the content of the FEM model. The model is mainly made in default steel and aluminum property. We do some simplification to the junction modeling. We add some rigid bar coupling between some systems, but on some other we replace junction by bolted points. In FEMAP it's described by C-bush. So for some part of the system we assume continuity of motion between, for example, welded part. And we also have added the floor in concrete, and we just limit to some piece to make it computationable. And the floor is described by a concrete plate element attached to the machine feet. So this model has been analyzed. See some finite element mode here. And then what is important for us is to convert this model into SEA. And this is done by our technology of virtual SEA that transform the FEM statistical information into SEA parameter, and then you can really have the quality of the FEM within SEA describing the effect of the geometry at low frequency. Or typically how it works, for those who don't know this technology, if we excite the finite element model at a set of nodes, here you have a mapping of nodes. At each node we compute frequency response function in the three direction, and then from this, for each point being considered as an excitation point or an output point, we compute a large matrix of frequency response function. And this large matrix of frequency response function is first projected in the direction of maximum mobility to associate to each node a scalar value, and we do the partition of this matrix into group of nodes. And at the end, as soon we have substructuration in a rather automated way, we can calculate the statistical frequency transfer between what we call now subsystem, and then derive all SEA parameter. At the end, we have an SEA representation, that means an energy model, which has the same quality than the finite element model. And best, it's compatible with classical analytical SEA modeling. That means you can expand your model to high frequency using an internal analytical representation in each of the virtual subsystems. So in that particular case, our model is running from typically 0 to 11 kHz to cover the 10 kHz bandwidth, and then our model can be run nearly on the full range of the applied force. Now we go to the model, and first we will see how to apply the force, the shock force. And if this shock module is enabled, this function is activated in the menu solve, the LMPS shock solve. But prior to apply a solve, you need to put some force, but I will add a load case to start from scratch. We can change the name of the load case. I call it video demo. And if shock module is activated, we have some shock sources. This first one is for specifically pyrotechnical cut of the system for example, stage separation in a rocket. You have a second one, more general, which is a pyro, we call it point pyro sources injected power. This icon is used to convert a force applying time domain to injected power. It is what we will use here. And we also have a clamp band injected power. It's when the satellite is attached by a clamp band to the stage, and then we can predict power injected from this system. And also very specific sources called thermal noise sources. If, for example, plate is distorted because temperature is increasing, so there is kind of ovalization, at the center time you have a relaxation of the motion, it generates some noise, and we can predict it from the sources. And in the most general cases, when we need to specify, we start from specification of shock environment. This specification is delivered in shock response spectrum format, SRS, and then we can directly apply this specification, SRS, to deliver a time history from a CA model, or you can also apply an acceleration constraint to the plate in the time domain. So you have many ways of providing the excitation to the system. In that case, because in the shock machine we do some testing and measure the applied force from the mass that is falling down, we will use this pyro shock sources injected power. We apply it, and before to apply it, we see we need to select the force in the list. So we have to first go to the database and add a time history force. If it is not present here, we can just go to Spectra, add for new time history force. And in that case, you have what we call the pulse generator dialog box, which opens, from which you can, if you can use predefined force profile. The most general one is a general pulse. You can use some formula. We have some syntax we can apply here to create some specific formula, or you can simply import from text, is what we will do here. And in that case, I will just go to my directory where I have loads of force. I import it, and now you see that the import forces have been scanned at 250 kilohertz. We see that the dynamic range of these forces is quite high, and higher than the accelerometer dynamic range, which stops generally at 70. And above 20 kilohertz, typically we expect background noise because there is a force is too low. And then obviously the limit of the calculation of the acceleration, the validity of the measurement, the limit of the measurement is about 20 kilohertz. So we will here down sample automatically this force to 35 kilohertz to fit our 16 kilohertz bandwidth, and here to compare directly the RMS value of the acceleration, I will scale the number of samples to 4096 sample. Why? Because in that case I have 170 milliseconds compared to 112 milliseconds for the measured signal. So practically the RMS value are comparable between measured and synthesized LMPR data from this setting. Changing the size, you change the resolution, which is automatically recomputed here. And then I click OK, and I have this signal here available in the time history. So this is this one, and you see this pulse, which is a pulse we are using. This pulse is 65,000 Newton. If I make a zoom on it, you can increase clicking here, and you can, alright, you see nice pulse, very smooth. Okay, now how to use it. when you have C-Shock enabled, you have an extra menu here where you can select shock sources, and we have different kind. What we use here is a classical point force, but we call it pyro sources, point pyro sources, because here this point force will include time data, and these sources are converting an excitation term in the time domain from into power, to ejected power. And I will select the forces I have just created now. Click OK. I just verify it's a spectrum time, it's the right one, okay, 60,000. And now I connect it to the excited panel, which is this block here. Call it side sidewall side table. I call it side table X plus because it's oriented in the positive axis, and I connect it. Okay, when the connection is opened, connection dialog box opens. I have to set the orientation of the force. As default in SEA, with the direction are energy direction, that means flexure, shear, and extensional. Flexure is for thin shell is normal to the shell, and shear and extensional are parallel to the shell. Extension is normal to the excitation point, and shear is perpendicular in the plane of the plate. Nevertheless, here this is a very specific point, so I click OK in that case to create the connection, because the node, as you will see, the transducer and the force impact point is just here at the interface of the table and the sidewall. This node is that one. Is a node 16052, just at the intersection line. And we need this value because this value will be more representative in terms of mobility. So I just click here and I select the node 60052 and not the mean value of the subsystem. In practice, when clicking here, if I click using the average mobility of the plate to convert into injected power, the force, here I will use the input mobility at this particular node, but in the direction of principal mobility. The fact is, here I have two thick plates bolted together. One is 30 millimeter, the other is 50 millimeter. The side block or the side table block is 50 millimeter. And we are just at the intersection, so we don't really know the orientation of the drying point mobility, and regarding measurement, it's pretty sure that we need to use the right direction of excitation. And for that, I will click in narrowband, use narrowband. What it means, it will in real time recompute the drying point mobility tensor, XYZ, with 9 component, and it will project the forces in against this tensor in order to compute in the direction I've defined there. And of course, if I put some percentage in X and Z, it will change the orientation of the force. And here, because it's an X force, we'll use the right drying point mobility regarding the excitation of the force. And we will see that it makes a big difference. Okay, by clicking in here, I can compute the injected power. You see this result. And if I compare now with what we have directly measured from tests, which is here, I have to look power. It's a point M1, and we compute from Fourier transform the injected power, the real part of injected power at that M1 point. You see that you have a good approximation of the injected power in the X direction. Due to the downsampling of the force, we have no more energy above 16 kilohertz. So I set up the most appropriate calculation, that is narrowband, and the node number. Now I can make a solve. A solve, classical solve, SES solve. Just have a look of my response in terms of acceleration. Okay, you see that this is most excited subsystem, the sidewall plus. This is the less excited, which is the concrete floor, the furthest from the excitation, and of course the more massive concrete floor. And then these data are roughly corresponding to what I measure in test. In that case, there is a test at a distance, reference node, show a reference node, and we have one node near the accelerometer M8, and then I can compare the acceleration at that point with the measurement at that point in terms of RMS acceleration. So file import, and then the acceleration, the mean acceleration are here. Mean RMS acceleration, not that one. Okay, this is the acceleration, and my here it's the response of this panel, which is thinner than the other. 15 millimeter is oriented on y-axis, and you see the prediction is pretty good. As you see, there is some offset in terms of frequency, so we don't know if it is a statistical effect, because in the virtual model all modes are really occurring. That's the goal of statistical excitation. Or if it is a bolted condition, which is pre-stress in bolt that shifts the natural frequency of the wall assembly. The fact is the magnitude order is correct in terms of RMS value. For both structure. If I look at RMS value, plot, we select both plot, and you see in terms of RMS 47 meter per second, 41, so there is less, about 10% uncertainty on the RMS value, and in dB of course it's very, very small, about less than 1 dB, typically less than 1 dB on the RMS value. So you see the prediction is quite good. Now we want to perform a shock, so for that we need to use the LMPR shock solve, and prior to this to define where we want to reconstruct the shock. So we can reconstruct the shock on the table, and we in that case I will declare my table as a LMPR receiver, set as LMPR receiver. LMPR, it's the name of the algorithms that make this time domain reconstruction possible, and then I set it to this the table, and on the table I want to reconstruct at a particular point, and that point, for example, is near from M3Z, so we can reconstruct on this point because there is a measurement point there, and we can compare obviously with the test result. And then I will go to LMPR shock solve, call this menu now, and you see that it will open a dialog box. And from the dialog box, I have to set up. First tab of the dialog box, you have explanation about the reconstruction process, which is relatively easy to understand. You have a time force that injects power on the structure, and we compute SEA, frequency response function, from this force. And we apply directly the force to the receiver to perform a complex response, and we scale this complex response to the value of the CIFRF in order to make it complex in the frequency domain. And after that, we just make a product of convolution between the force and the receiver and invert it in the time domain. Typically, we can add dispersion of the wavefront because from source to receiver it takes time. Generally, because we don't really know this dispersion time, so it's a parameter you can play with just to smooth a bit the wavefront, but on experience it is not so important on SRS, but peak level of the time history could be smoothed a little bit by this modal propagation. In terms of transfer, we see directly the transfers that are used, mainly the flexural transfer here, and the extensional transfer and shear transfer are just really high in frequency because the extensional mode and shear mode are really high frequency mode, not handled by the virtual model, which works in the direction of drying point mobility. If we want to add the dispersion, we can work on the table, and adding the table is we can add 0.5 dispersion, for example 5 meter, because we don't really know 1 meter, let's say 1.8 meter. 0.8 because the table is really separated into two parts, so we expect reflection and the board connection, and then on average high frequency to go from one side to another side of the table is about 0.8 meter. And then the shock spectrum parameter are default. You can change them, but this is default for space community. 10% Q factor. Here we compute per 50 Hz band. Absolute acceleration, and we don't want to plot in G because all the data we store it's a meter per second square. And then we use absolute damping model, and that's it. The signal is not large, we can stay as it is, and this is a window that shows you the various parameters of the synthesis. We have the time domain will be synthesized on 4086 points with a resolution of about 8.5 Hertz, and highest frequency will be 16 kHz in that case, so 6 kHz above the limit of the FEM transfer. And I click OK. Yes, I have to create some point inside the receiver for the reconstruction. So this is the size of the receiver seen as a rectangle, and we can add observation point, and generally the node M8 is about, this is the coordinate of the point M8, so it's 0.55, 0.62. And in that case, for the force, it will be, we have no phase, spatial phase for the force, because it's arrived on the boundary of the subsystem. And we will add several forces and randomize their coordinates just to make an average and stabilize our transfer function, LMPR, what we call the LMPR transfer function. And we will use the damping of the subsystem. This is here the damping will be assumed to be modified on the fly to make quick calculation on damping effect. Generally, the damping effect is mostly in the level of transfer function, so it is not so effective as you can believe at first glance. Now we can back under the tab transfers. So the default transfer which is stored here is mean acceleration value per unit force of the response of the table. In that case, we want to specify the response at the particular node where is M3 or Z in that case, normal to the table. And for that, we have previously exported the acceleration spectrum at that particular reference node, and I re-import it in that page by setting the maximum bandwidth I want to cover, 16,000 Hertz, and then I import this file from the disk. And here the storage folder is that one, and this is the last I modify. This is that one, the node 17848, and that this is this particular transfer. And then everything is okay. I set the dispersion of the table and compute it by LMPR. This is the standard deviation over the fourth point, which is about 2 dB maximum at high frequency. LMPR time history is here, and this mean SRS in meter per second square is here. And I will export under text file in this video demo directory the file. So per default I can export only the flexure, all point, or just one point. In that case there is only one point. All excitation have been averaged. I store on disk SRS spectrum, and I will store in video. So on this disk, I think it is stored in video. No, not here. In studies probably, shock machine. No. Should be that. So we store in this video anyway. And in this video demo, I will export SRS file, and then the time history. All right. So now the work is done. What it gives, I have to look at these two files, and in the database I have stored the time history data from test in the different direction. Recorded on M3Z, for example, it's force, so I can plot this time history, and from here I will import what I've recorded in video, and you see the two signals, the synthesized signal from time acceleration. I mask it, right? So you see a big negative peak there, and probably it's coming from the fact I have not enough delay my signal. So I would just make this first comparison, then I go back to SRS. I have also the SRS in the different direction, recording from test. XZ is here, and if I import the calculated SRS, you see that we have a pretty good agreement, except in the low frequency range, where it seems a bit over predicted there. But where it's maximum, we have a nice correlation. Now, if we put a little bit of scattering on this prediction, I go back to the model and go back to LMPR shock solve. Now I'm setting the dispersion to 1.5 meter, which is one wave go and back from boundary in order to build a mode. I click OK and recompute the LMPR time domain, but I forget to set up. I forget to set up the transfer to the measure value. So import. Here I have to import this model propagation set receiver definition. Okay. And now I can export the data to video demo. Same name. And time domain. How to see, we will look SRS first. In that direction. Importing the LMPR calculation. LMPR calculation is in video directory. Make a mistake somewhere. Then I will go back to model, recall my calculation, text file, SRS spectrum, all right, and LMPR time, okay, and now go back to data. This is shock, SRS shock, right? M-Z, edit, plot, file, import, video, LMPR time, SRS. Okay. So you see, with the dispersion, the agreement is improved, and the dispersion I've set up is just twice the length of the plate in the maximum direction, that typically 0.7 meter, 0.75 meter, so multiply by 2, 1.5 meter. And in the low frequency, we have a bit of a prediction. But there is no table mode in this area. First mode are about that frequency, so for the first mode, it's always very, very difficult to get a good result. And then we just now going to time history acceleration. Looking now at M3Z. Import from file. No, just plot, sorry. And file import LMPR time, and you see we have pretty good agreement in terms of time history. We also see that the fact we overpredict is most probably we have a little bit too much damping in your system at low frequency, because we still see mode oscillating while they are quite much damped in the model. So mainly it's a problem of damping, the over prediction at high frequency. So typically it's what we get for vibration. And then I stop this.